Okay. Uh, First, I'd like to thank organizer for providing me the opportunity to give a talk on this topic in this nice conference. And I'm going to give a talk on information-theoretic approach to inhomogeneous cosmology. This topic is actually based on only classical cosmology and is not directly related to quantum theory. But I hope this may be helpful in understanding the connection between information theory and gravitational theory. This is plan of my talk. First, I will explain what the averaging problem in cosmology is. And next, second, I will address basics of averaging of inhomogeneous universe, which our approach stands on, with the definition of entropy and the back reaction. Next, we will explore the temporal behavior of the entropy with the estimation using linear perturbation theory of Friedmanian universe. And finally, I will give a summary and conclusion. First, I will explain what the averaging problem in cosmology is. In standard cosmology, cosmic inhomogeneities are treated only linearly. That means this is at the epoch of recombination, and the universe evolves. But inhomogeneity are treated only linearly, so the background universe is unchanged. But in actual inhomogeneous universe, inhomogeneity grows because of the nonlinearity of Einstein's equation. And so the actual universe is like this. And so it's highly non-trivial whether we can identify with real inhomogeneous universe, which is averaged over some large scales as a Friedmanian universe model. In other words, the time evolution and the spatial average, these two operations do not commute in general. I will later explain this in more detail. And this fact, the presence of inhomogeneities, may lead the average properties of realistic inhomogeneous universe to deviate from those of Friedmanian universe model. And this implies inhomogeneities could be an alternative to dark energy for cosmic acceleration. And there are some works on spatial average of inhomogeneous universe and back reaction. And this means how the effective scale factor behaves. And the work by George Ellis in 1984 is, this is, I think, the first work which points out the non-commutativity between the spatial average and time evolution. And there's some other, this is a Japanese Futamase, Toshi Futamase, and Ruskata in 1986 or 7. And these works depends on standard perturbation theory from standard background Friedmanian universe. But after Burhat, after this work, they do not assume background space-time from the beginning. Sometimes the conclusions of the effect of the back reaction method dependent, and this means the conclusion depends on a choice of hypersurface or the way of spatial average. And next, I'd like to explain the basics of averaging inhomogeneous universe. And now this may be called now Burhat formalism or Burhat averaging, and these guys. First, we choose co-moving and synchronous coordinate with the line element, and this Gij denotes the spatial metric, and the co-moving gauge. And now we consider the matter as irrotational dust, which affords a energy momentum tensor is like this. And then we can write expansion rate is which is given by covariant divergence of for velocity, and this G denotes the determinant of symmetric, and then we can write continuity equation and the Rayleigh-Audry equation and Hamiltonian constraints. And I forgot to write the definition of sigma. This denotes the shear scalar rate squared. And we define a spatial average of over a compact spatial domain on a constant time hypothesis. And then we can write commutation relation between time evolution and the spatial average. And this right hand side includes the expansion rate. And applying this commutation relation to the density field, we can write this. This immediately is the average continuity equation. Now we focus on this commutation relation. We can naturally define entropy of cosmic field. This means that the difference of these two quantities. One is evolution of average density field, and another one is average after evolving the density field. This the difference of the two quantities generates the entropy, and so we put here entropy production per volume. And interestingly, the answer for the this is some function of energy density field, and the answer is relative entropy. Sometimes relative entropy in information theory, and sometimes called Kullback-Leibler divergence, and written by this formula. And in fact, this quantity is positive definite, and exactly zero if and only if the density field coincides with the averaged value. And this quantity actually measures the two distance between two distribution. And next, we move to commutation relation for the expansion rate, and this is written in this form. And inserting the Ray-Choudhury equation, we have averaged Ray-Choudhury equation, or maybe called generalized Friedmann equation. And the difference from the standard Friedmann equation is the back reaction term, which includes the fluctuation of expansion rate and averaged shear rate squared. And this part is positive definite, so the this will play a role of acceleration, cosmic acceleration, and this corresponds to the deceleration or maybe additional dark matter. Let us explore the temporal behavior or time evolution of the relative entropy. The time derivative of the relative entropy is by construction the correlation of density fluctuation and expansion fluctuation. And if we consider cluster or over-dense region in the universe, the density fluctuation is positive and the expansion fluctuation is negative. And if we consider void in cosmic void under dense region, the density fluctuation is negative and expansion would be positive. In any case, we can expect the time derivative of the entropy would be positive. But maybe depends on the initial data. Next, I'd like to mention the time convexity of the entropy. That means the positivity of the second time derivative of the entropy. This is actually written in this form by using Ray-Choudhury equation. And these terms are all positive definite. And this includes the back reaction. And here are the first time derivative. And so, if the back reaction term is positive, then the second derivative is positive at an instant when the first derivative is 0. So the after this time, the first derivative always stays positive thereafter. Now, the first derivative is we know the written as the correlation of the density fluctuation and expansion fluctuation, and this is intuitively positive. And also we found second time derivative is related to the back reaction. And if the back reaction is positive, that means behaves as dark energy. The time derivative becomes positive after sufficient time. And this means a temporal increase of the entropy and the dark energy-like back reaction are somehow linked. And we also have some concrete evidence and mathematically rigorous proof for the temporal increase of the entropy has been given with linear perturbation of Friedmannian universe and a spherically symmetric Lemaitre-Thomson boundary solution, and also behavior similarity using focusing theory. Finally, I'd like to give an estimation of the back reaction and relative entropy with the linear perturbation. This work is done by my colleagues, Lee Schwartz, and this is metric, part Abbott metric, and this H is linear perturbation, and we only consider scalar mode for a special flat Friedmanian background, and the solution is factorized into temporal part and special part, and if we neglect the decaying mode, the back reaction can be approximately written as this. Next, we give I'd like to give an estimation of the relative entropy with the linear perturbation, and this can be written at a glance. This may be the entropy decrease, but this is divided by the volume. So if we consider entropy itself, this is increasing, and this part is positive definite. And in fact, this part can be rewritten into the wild curvature invariant and the back reaction. And I don't know the physical reason, but this is also some implication for the wild curvature hypothesis. And also, this is entropy itself, and first time derivative, and also second time derivatives has a similar formula. I'd like to summarize my talk and give concluding remarks. A Abelian inhomogeneous universe model has been considered in the context of the dark energy cosmology, and measure of inhomogeneity naturally arises from the averaging formulation. And this measure is actually a Kullback-Leiber relative entropy in information theory. And this relative entropy is increasing function of time, and at least after a sufficient time. And this temporal increase is somehow linked to the signature of the back reaction. And also, we have obtained the result of relative entropy is given as a sum of wild curvature invariant and the back reaction to the leading order in perturbation. Thank you.
Thank you very much. Is there any question? Okay. Oh, here we are. Yes. But
Fisher information matrix. Hmm? Maybe the Fisher information is defined by the some derivative of probability density, right? If we consider, this is Kullback-Leiber, and the infinitesimal deviation of the two distribution is written by Fisher information matrix. Yes, yes. So we can define Fisher information from this definition.
have time for one more question, if there is any. Okay, if not, thanks the speaker again. Thank you.